hear me? Okay. So, okay, thank you very much again. So here I am. Now you can see me maybe, I don't know. Today I'm going to talk about an Elo-type rating model. And this is a work which has been ongoing for, I think, 2 or 3 years. And a couple of people involved, there's Bertram, is actually sitting here. Josephine Evans, who visited us a couple of weeks ago, she will come next week. And there was also a PhD student, Marie-Therese involved. Unfortunately, he left academia. He was one of these PhD students where we were very lucky. He came to visit Bertram, and after the visit we had one paper, so this was a really nice project together. And so I'm going to start today by explaining you a little bit what the Elo rating system is. So if you are playing chess or if you're in soccer, then you should know the system, or at least you have heard of it. And I will explain at the beginning, okay, what's the discrete setting and what is used in soccer and what is, well, actually, I should say football, since I'm in the UK, what is used in chess. And then I will talk about a continuous version of this model, a kinetic model, which was proposed by Juncker and Chabin. I think, if I'm not mistaken, it was 2016. And the nice thing about the model by Juncker and Chabin was that they could show that if you assume that you have infinitely many players and you have infinitely many collisions, because what our games are now are collisions, like we know in kinetic theory, then what you will observe is actually the behavior that you want. The Elo rating system, what the idea is, you have a rating and you have an underlying strength of your player. And the rating should represent your underlying strengths. And in the long-term run, you wish that the ranking converges towards the strengths. And when Elo, so the name Elo comes from the person who proposed it, it was Arcad Elo, he was a physicist. When he originally proposed this model, he tried to prove, okay, this is a good idea, so this is going to be a good representation of the player's strengths, but up to that point, there was no proof. I mean, still we are in a very stylized setting. I will explain to you what is done in practice, what Juncker and Chabin proposed. And then in the second part, I will talk about generalizations of this model. So in the original model of Elo, we have players, and as I said, they have an underlying strength, and the rating or ranking should represent the strengths. And what usually is assumed is that you have a strength and that this one does not change. So you're born to be either a chess master or not, which, let's say, it's a little bit questionable. So what we worked on was a generalization of this model with dynamic strength. And I will tell you in the second part how this generalizes and how it changes the result that Juncker and Chabin obtained, and yeah, how you can play a little bit with that. Okay, so let's get started. First, Elo rating system. As I said, some people know it, but just to give you an idea of what I'm talking about, we have, as I said, there was this physicist, Arcad Elo, and you assume that your players play in a zero-sum game. And each play or game is a collision, so to say, model. And after each play, you update the score or the ranking of all the players. And he proposed this for chess. So it was used in chess a lot. And I will explain on the next slide how it's calculated. But nowadays, it's really, it has been adapted for many, many other sports. So you can look at online gaming, American football, soccer, FIFA is using it. Yeah, even Scrabble, apparently. And this is, for example, the table that you can download. And in 2018, the FIFA adapted their ranking. So there used to be a FIFA ranking that used a different type of ranking. And then they moved, in 2018, they decided to go to Elo because it's better. And then you can see how, like, the different countries of game, the soccer teams, how they are ranked. So the UK is not doing too bad in this ranking, but I have to say this is not really up to date, so maybe I'm wrong. There are 5th at the moment, but that was at least 2 years old. I have to check. Austria is way down. I don't even know where it is. So yeah, but you can have a look and you can find these tables online. And this gives you an idea who is going to be a better team or who is going to be a stronger player. And if you do this in chess, then the FIDE is doing the following. So we have our rankings, and in the throughout this talk, I will denote rankings of 2 players always by capital R. And if you play, then you will update the rankings. And the FIDE, what it usually does is it updates the rankings each month. So there are some live updates, but they are not official. So after each month, they publish the ranking of each player. So each chess player has a ranking. So I think if you're above 2,700, you're really good. You're one of the top. If you're above 2,200, you're considered good. If I'm not very good, but I'm not the expert. Anyway, so how do you update it? So we have our I and our RJ. These are the ratings or rankings of two players, I and J. And then you can define what looks already quite similar to a binary collision rule. So we take the RI and the RJ. So the post-collision or post-game ranking is my previous ranking. Then the Sij is the outcome of the game. So Sij is always a function which either takes the value, you get a certain number of points. In this case, for the Elo, you get 400 points if you win, at minus 400 if you lose. The EI is the expected score of the player. So EI now says, okay, I'm calculating the expected score of the player depending on the difference of the ratings. So what this tells me is I'm going to, if I look here, the EI depends on the difference between the RJ and the RI. So I'm now looking at a game of two players. If the other one is stronger, then the probability that this guy is going to win, or we would expect that this person would win because it's a stronger player, then you compare it to the actual score, you scale it, and depending on the difference, you update your ranking. And this number K is, if you go to chess, then it's 800 divided by M plus N, where N is the number up to all the tournaments you played, and M is the number of games that you play in the tournament. So in principle, what you do is, this term here says, you take the outcome of your game that you see, Sij, you compare it to expected score depending on the ratings. So what you would expect based on the ratings. And then the difference gives you the adjustment of the rating. So if the player underperforms, you're going to decrease the ranking. If the player overperforms or does better than you expect, you're going to increase it. And the K tells you how you tune it. In the FIFA, they kind of modified this. So it's not like a constant. So in the K here in chess, it's 800 divided by something. So in the FIFA, usually you update the rating depending on the importance of the game. So if you play National League, it's 15, but if you're in the World Cup finals, then it's 6. Okay, so there are different modifications. Also, the expected score here, it's 600, it's a scaling, but so this is what is used and it has been adapted for different settings. But the idea is, okay, we have an underlying strength, we have an outcome of your game, and we have an expected outcome, which depends on the rankings. And based on these three quantities, you're going to adjust your rankings, and you hope that in the end, in the long-term run, the rankings will converge to the strengths of the player.
Sorry, what is Sij?
It's the outcome of the game. Sorry. And this is it. Next slide is it. So now, as I said, it already looks a little bit like a binary collision. So Jabin and Juncker had a look at it and said, okay, let's do it in the kinetic setting. So now we have a bit more in mathematical terms, no more 800s and 400s, because that's no good. So we have again the post-collision ratings. We have our pre-collision ratings. We have an update factor, which I now denote by gamma. I'm not going to assume that it's going to change. And now what we have is Sij is the outcome of the player. So if it's 1 if player I wins and -1 if player J wins. So, and the function B now represents the similar, this is this expected outcome that I already showed you before. It was 1 over 1 plus 10 to the power of something. I mean, in principle, you can approximate this by a tangent hyperbolic. So the function that we saw on the previous slide, this one, if you scale it correctly, then you end up with a tangent hyperbolic. So you get a -1 or a +1. And so it's a function of the difference of the ratings. So Sij, as I said, expected outcome. The Ri minus Rj gives me so Sij is the outcome of the game. B is the expected outcome. You compare it, you update it. What you usually assume is that the Sij it's a random variable. So it's the outcome of your game. And you assume that in expectation, that it depends on the difference of the underlying strength. The underlying strength is something which is unobservable. It's given. So I have a distribution of our players with respect to the strengths, and I want that the ratings are in the end converge to this underlying strength. And I assume that this underlying strength is given and not changing in time.
So the EIJ and in the previous slide, so this is hidden in this expectation?
You mean, yeah, no, this here, yes, it's somehow in.
Sorry,
Yeah.
this,
No, it's not.
Now it's in the
in the SIJ, sorry.
Okay, sorry.
Okay, so this is the update rule, and this is the setting. So now what you assume, or if I look at the binary updates here, what we see is, first of all, we have conservation of ratings. So the sum of the post-collision ratings is the same as the sum of the pre-collision ratings. Okay. The expected update, so if I take the expected value of this update, so of the RI, my new rating, then in the end, if I assume that the E of the SIJ is equal to, we said is equal, so we assumed that it's, sorry, here we go. It's just a function of the underlying strength, so B of rho I minus rho ij, then I will get that this term is going to vanish if the E of Sij is going to be equal to the B of the Ri minus Rj. Otherwise, I will always have an update. So in this case, you will see that you will get a stationary state if your ratings really represent the underlying strength. So this is the main, so to say, goal, because you want that in the long-term run, that your ratings converge to the underlying strength. What are properties of this update? The other thing that you might see is, I mean, the updates, they only depend on the difference in the ratings. The whole system is translation invariant with respect to shifts. It's just to kind of mention it here. And then what you can do is you can, that's what Jung and Jabin did in their paper, they derived an equation for the distribution of players F. So F is now a function with respect to R, my ratings, rho, my underlying strengths, and T. And what you can see is in this function, we have a transport term, and it's only transferred in R because we remember the strength is rho is given, it does not change. So the distribution of my players changes in the rankings depending on this operator. So here I have an operator which exactly mimics what the binary collision rule does. You compare the difference of the current ratings of the player with the underlying strengths, you integrate against the density of these players, and you can also introduce something which they call a weight function, where you say, okay, what's the probability actually that two players play? Because if you otherwise, I mean, if you set it to 1, then this means everybody interacts with everyone. However, if you would assume that you can only play against somebody who is sufficiently close to you in rating, you might want to introduce this function which tells you, okay, I can't play, I mean, I should not play against the chess master because I have absolutely no idea what I would be doing, so that's a waste of time for both of us. So here you would include this weight. So this was in their original paper, and what they did then was, okay, they analyzed the behavior of this equation. So you wanted to know what are the stationary states of the Fokker-Planck equation, and it's a really nice paper. So if you're interested in that, my students always like it. What you can show, for example, you can define a relative entropy. So if you define, for example, this relative entropy here, and you assume that your interactions, they are positive, so there's a strict lower bound, then you can show that this entropy is decaying. You can also prove that your function f converges to something that this here is, your system is translation invariant. As I said, you can always shift it. So you have to take this into account when you calculate. So it converges to a delta Dirac along the diagonal. So your ratings will converge to the rho. However, it has to be shifted in a sufficiently smart way because of this translation invariant. So the M1 and the M0, they are the original mass and the original first momentum at time t equal to 0. So this is just a necessary shift to get it back to your reference frame. But however, what they proved is that in the long-term run, we will converge on the diagonal. If everybody interacts with everyone, you have n infinity number of games and times tend to infinity, and this will also go exponentially fast. So first proof, and this was actually quite nice. because if you want to introduce a rating, one of the questions, this was also what our Elo said, was, okay, how do I have to choose a rating? How do I make sure that this rating really represents what the player, so to say, how strong the player is? And I mean, in this idealized setting, one can say, should converge to rating. But yeah, I mean, if you want to look at a picture, then in this case, you do some simulation. We started out at the beginning, the players were equally distributed over the entire space, 0, 1. So, and you can see after time t tends to 0, they converge all really nicely along the diagonal, and you get this convergence of the ratings, which you see on the y-axis, to the strength, which is on the x-axis. So you really see this very nicely. You also get exponential decay. So this was the setting that Juncker and Chabot had a look at. And what I'm going to talk today is how we can assume or we can generalize this, because we had this function rho or variable rho, which is the underlying strength of a player, where say a player is going to, but you might want to say, okay, I'm not playing or performing equally well on each day. I might learn something in encounters. So if I play more, I should get better, at least I hope. In mathematics, you also hope the more you fail, the more you learn. No? So we thought, okay, let's assume that rho is not stationary, but it also changes in encounters. So now we're not only playing with Ri and Rj, which are still our original ratings. So nothing has changed in the first equations. You have the Sij, which is the outcome of the game. You compare it to the expected outcome based on the ratings. This is totally the same. But now the rho I and the rho j, these are my two variables which represent now the strength after an encounter. They change, and now you have a bit of modeling freedom. And if you're a mathematician, we thought, okay, let's include a couple of learning mechanisms here. So the function h is my learning mechanism. And the ethers, they are random variables, and they are just daily fluctuations, because yeah, there are some days where I give better talks and some days where I give worse talks, and the same is for games. So there are some days where chess players probably don't play that well. So these are just the daily fluctuations. And then for the learning, we say, okay, there are two terms here. The first one is a learning term, where we say that if in each game as I play, then I always learn something, I gain something, and it depends on the difference of the underlying strengths. And the one possibility, but please, you can, there's not a freedom in it, but we said, okay, let's assume this. So it's a positive function. So both players learn, and the individual with that lower learning level learns more, while the one who has the higher one learns less. So this is one of the assumptions. The second one is the H2 term. Now it takes into account also the outcome of the game. So what you do here is that if you play and you perform badly, so if you are actually the person who is supposed to win and you lose, then you lose confidence. And if you win and you are supposed to win, you gain. So this is kind of, I'm pushing a little bit, saying, okay, you are supposed to win. And if you don't, then yeah, you somehow lose this self-confidence. So this is hidden in this function h2. So we assume for the time being, let's choose these two functions. And you can play a little bit around how they look like. This is h1, and then you can choose it. But the outcome of the whole thing is that what can happen now is that you can lose strengths, and you can also gain strengths depending on how you choose the alpha 1 and the alpha 2. You can also make that it always increases. So if you choose, for example, the loss term, so I will talk about at the very end for the case where we only have learning in games. So if I said beta equal to 0, then I would constantly learn. I mean, this is also very stylized, but let's assume the world is very good. Okay, so then you can write down and start by writing down your collision operator. And also in this case, what we did was, okay, you write down your Boltzmann equation. On the right-hand side, you have a collision operator. You put in the binary interaction rules. And we introduced also this interaction function. So in this case, there are two choices. What you usually do, as I said at the beginning, it's the probability that you play. So one of the The most likeliest one is that you say, I'm only going to play if you're sufficiently close, but you can also take any more smooth version of the whole thing. We have conservation of ratings. So in Turtle, I also have conservation of mass for the F gamma. And you can have a look at the moments. So if you define the moments of the function F gamma now with respect to the ratings, then you can see that if your initial moment is equal to 0, then it's conserved for all times. However, the second moment, it's grows at most linearly in time, because this is due to the fact that you have these learning terms. So this is the first one. The same is for the moments with respect to the row. So what you also observe here, that you have these learning mechanisms, and what you also can see here, that you have almost at most linear in growth, linear in time growth for the first and the second moment. So you can do formal calculations to just have a look at the moments what's going to happen. However, Boltzmann equation is not so nice, and you can go back to all the nice works of Toscani and look at the equation in the quasi-invariant interaction limit. And what you assume here is that you let the interaction, so that this update parameter gamma tend to 0, the diffusivity tend to 0 in such a way that this fraction here is kept at the constant, which I denote by sigma. And then you can derive a similar equation as Juncker and Jabara did. So if you now look at this equation, the first term is exactly what we had before. So the A is this term that Juncker and Jabara had. So we have now a transport in the ratings, but we have also two more terms which come from the fact that you learn in games and that you have these fluctuations in your daily performance. So the fluctuations in the daily performance, not surprisingly, give you a diffusive term, and you might want, if you want to include this interaction function, then you have a diffusion coefficients which depend on the W. For the term C, this is now your term where you have the change in the ratings due to these learning mechanisms that we introduced. And here what you see again, it's just like, yeah, it has a very similar structure. You just look at the function, integrate it against the density of your players, and this gives you the transport advection in the row direction. And the first thing, so when we started on this model, first question was, okay, what can we say about structure? So can we say that, for example, does it have a solution? What can we say about the moments of this equation? And so, first of all, if you look at the moments of the Fokker-Planck equation, then you can look at the first moment with respect to the ratings and the strengths. So the first moment does not change in time, one can prove that. However, if you have, if you look at the first moment with respect to the ratings, you see that the strength increases all the time. So you can't expect that you, first of all, to have any steady state. So if you look at long-term behavior, then one always has to kind of take care what equation you want to study. And so due to this translation invariance, what we decided is that we look at the shifted function. So in this case, what you do is you can, since you know how fast your ratings grow, you can always shift them back to your reference frame. And this is what is done here in this second box here. So I define now the function g, which is just the problem that I shift back to the reference frame. And if you do that, then you end up with an equation in g. So now g is my function which is shifted back to the reference frame. And what has changed here is actually just the learning mechanism. So this, now I have an operator C tilde, and the C tilde is chosen in such a way that I will have a stationary state, or at least I'm staying in my reference frame, and I'm not, my knowledge is not increasing all the time. I mean, the diffusive term and the transport in rating direction is still the same. So this is the problem that in the end we're going to study. So I'm not going to study the original problem in F, because I would have always this linear increase in time of my knowledge, and that's in any way questionable. One can discuss. So this is a favorite question. Don't you want to have any decay, which is also true. But for the time being, what we assume now is, okay, I'm shifting it back to my reference frame. Let's have a look what we have asked.
Sorry, what do you assume for W?
In this case, it always had to be a sufficiently smooth function. So I think some definitely not the indicator function. So to do the whole thing you needed, I think, was it something like this exponential C infinity with some bounds, but I have to look it up.
The alpha is the same.
Which alpha, sorry?
The alpha in front of the, for example, the third line.
Yeah, the alpha, this is the parameter which comes, these are the two parameters that you have from the learning. So this was this alpha. Yes, and the learning is the one that always pushes your knowledge level up.
So you shift back with respect to this learning.
Yeah, exactly. So what can you do? And I'm not going to go through the details of the proof, but yeah, you can spend a couple of pages. And first of all, you have to decide how you're going to pose the problem, because I mean, one idea would be to study it on the entire domain, but that we couldn't manage what happens at infinity. So we posed it on a bounded domain and added homogeneous Neumann boundary conditions to make sure that the total mass is conserved. So if you have a couple of assumptions on your domain, if your initial data is sufficiently nice, I think, does it say somewhere, yeah, what the W has to be? Then you can prove that there exists a weak solution and that everything is nice. So we could prove this existence. It's in principle, what you have to do is you have to regularize your problem and then do a couple of a priori estimates, pass to the limit, and you're done. But it's a short fixed point argument. Yeah, a little bit of technicality. I'm not going to go into the details, but in principle, you can show, okay, there exists a weak solution in time.
So Marie, here W no longer needs to be even, just needs to be positive and smooth enough.
Does it have to be even? That's a good question. I think we always assumed that it has to be even, but I have to check. It definitely has to be nice and smooth. Okay, so but before I'm going to talk, so now we know we have existence in time. Do a long proof. I'm going to show you how does the model behave and what are we going to expect in the simulations. And at the end, I will talk about the long-term behavior, because if you look at this equation, then one might expect to see something which is, since you have the diffusion, the question is, what is the stationary state of this equation? So if you drop again all these learning mechanisms, we saw this accumulation along the diagonal. If you add these learning mechanisms and you add diffusion, then what you see is some blurring around the diagonal. And well, I mean, I'm not a hyperperceiving person, but it kind of looks cute, and we ask ourselves, can you prove anything about stationary states? Is there, yeah, I'll show you in a second how it looks like. But yeah, can we say something what the stationary state of this equation, a little bit simplified, looks like? And so far, we had put a lot of work in it that we still don't know any explicit solution, but we know a little bit. Okay, but how are we going to simulate it? So for the Boltzmann equation, we used just Bird's scheme. So you have a certain number of agents, you select them randomly, you let them collide, and so on and so forth. If I'm doing simulations of the Fokker-Planck equation, then what I usually do, or what I always do, is a splitting scheme. So you always do update in the ratings, you do update in the an update step in the strength. You do it in such a way that it's conserved. So you use upwind. I used finite volume schemes. Whatever you choose, I did strong splitting, but that's what I did, the simplest method, but just to get an idea what is going to happen. Okay, so if we have the situation where everybody plays everyone, so W is equal to 1, I'm not going to consider any special setting, then since we now, what we would expect in the shifted problem is not a convergence to the diagonal, but the convergence to the center of mass, which is a delta Dirac at 0.05, 0.5, because I assumed I started with a constant initial distribution on 0, 1. So the first picture shows you, okay, this converges in time to a delta Dirac right at the center of mass, of the initial center of mass. And it does it fairly quickly. We have some really nice exponential decay in time. If you add diffusion, so now I'm turning on this small diffusion term here, where I think it was 0.05, if I'm not mistaken, you see that you get something which does look a little bit like a Gaussian, so it's blurred out, so we get this kind of profile. We still get some exponential decay of an energy. And so one of the ideas or questions that we ask ourselves is, okay, can we prove something about the existence of stationary states? How should they look like? And if I have diffusion, can one use these ideas for hypercoercivity to say something? Because does diffusion in the ratings, so to say, give us this behavior, the observed behavior in the blur in the diffusion in the strength correlate to the blurring in the ratings? So that was somehow the starting point of the whole question. You can play much more with this model, and in this case, what we did is that we started out with two groups, which at the beginning I had, so now I have to figure out what I did. So we had ratings where we played a little bit with the interaction, but we assumed in both cases that you, in the first case, that you can't lose strength. So I set the beta, this was the second term. So if you interact with someone, then if I set the beta to 0, then I will always gain knowledge, but in the long-term run, I can't lose it. However, if I allow that individuals lose use confidence, then we see what's happening at the bottom. So what do we see here actually? So I have two groups. So if I just flip this whole thing, then you start out with two groups which were originally over and underrated. And you look what happens when you play with the ratings. And if you have a group which is overrated, so you start out with some group which at the beginning has a higher rating than it should be, and you only have limited interactions, and you don't have any corrections due to loss because you don't correct wrong behavior that you observe to this over and under rating, then what you see is that you can get very, very different profiles than here. So what's happening here is it corrects it a little bit, because you see that the ratings and the strengths, I mean, they're still not perfectly on this diagonal, but it's somehow, even if you started out with these two groups at the beginning, I think it was one here and one over there, that it kind of shifts it back, because this loss term or this beta term here, what it gives you is if the outcome does not match what you expect, depend on the ratings, then you pull the rating down. If you don't do this, then you keep this kind of ratings where, I mean, we have a group here on the top which has a rating of 0.6, it should, but the strength correlates to 0.2. So this is not correcting this kind of behavior, while if you include this kind of effects, then you can actually correct it. Can't prove anything about that, but yeah. You can also play a little bit. If you have a player which always plays a foul game. So if I now do a Boltzmann simulation, what I had here is I had 5,000 players and I selected one, and this player cheated and he always got more points than the others. Then in the end, my players, they converge to the diagonal except for this guy, which is this little star. So you can play a little bit around and you can just have this kind of cheating behavior also in your simulations. But I mean, this is just always, you start out with some distribution, you see how it behaves. However, if I now come back to analysis and say, let's have a look what actually my model is doing, then if I go to this rating model and now I'm turning off the beta, and I'm setting alpha equal to gamma, and this is because now we are in this last project with Josephine Evans, and Joe decided to rename the parameters, I'm sorry. What we have is, this is the same equation that I showed you for G, except for no loss of self-confidence, so you only learn. We shift it back, and the learning rate alpha is now denoted by gamma. And this is exactly what I showed you before. We saw just now in a 3D plot that I have now this beautiful Gaussian, which is centered around the original center of mass, which is 0.05. And these are my two operators. And the question is, okay, can I calculate now equilibrium solutions of this problem? And does there exist an equilibrium solution? I mean, I can simulate it and I can show you this thing. But what we did before was we proved there exists a time-dependent solution. ideally you would like to somehow start out with, okay, I assume this is the delta Dirac on the diagonal, which is kind of multiplied with a Gaussian on the in the or tangential component, and then put it in explicitly, but we never figured out if there is any, so we can't find an explicit formulation for the stationary state. So what we did then was, okay, first thing, can we prove existence of solution? And the answer is yes of the steady state. So this is hopefully a soon upcoming preprint. So if you assume that B is a nice smooth function, then you can prove that there exists a steady state solution of this two-shifted problem, which is a probability measure, and it has bounded exponential moments. So this is the one main theorem, and it took Joe a couple of pages of work, exactly like 10, to prove that this actually exists. So what we do know now is, okay, we have a time-dependent solution. I know there exists a smooth solution. I don't know that it's unique. So this is the one thing that we have, and it has certain properties. And what you can also, and this was this kind of interest that we got, or how we got to this problem, and these were the plots that made Joe most happy when I managed to get them, is that when she did the proof, she worked with the following relative entropy. So you look at the F with respect to the F infinity, which is now this equilibrium solution, and you weigh it with a function phi. And I mean, this is beautiful. And by the way, I missed the minus here, please. So it's exponential to the minus, otherwise this is going to be dead. So if you weigh it in a certain way, either with the inverse of your steady state, or with this phi, with a minus here, and you plot the evolution of the weighted relative entropy for certain values of beta. So, I mean, she used this weight in the proof. She couldn't give me, I mean, there were some, let's say, bounds for the beta and the gamma, and I played a little bit around. But what you can see is a staircasing effect, which is also observed in for hypercoercivity if you look at kinetic Boltzmann equations. So, one hope, or at least so far we have not succeeded to show anything. So if you take this energy and you try to prove to get any of this behavior, so what I learned from her is all the techniques that are available don't work because we don't have an explicit stationary state. So you can't calculate the F infinity explicitly. The equation in itself is nonlinear. It's a nice equation. So we have these two terms. We have the diffusion and we have the transport in the rho direction, but it's actually, the problem is that we don't get sufficient bounds at infinity to make sure that everything stays inside. So the nonlinearity is kind of giving a little bit of to the problem. Even so, in principle, it's not a really bad nonlinear equation, but all the techniques that we had a look at so far for hypercoercivity or using any of the results that we observed, exponential convergence towards the stationary state, we were not able. So we could prove there exists one stationary state. The numerical results indicate, okay, there's something very similar going on, but we have no idea how to prove it. And this is also how I'm going to conclude. Future research directions, yes, as I said, long-term behavior would be really nice to learn a little bit more how you can use these techniques. So far, to my understanding, it's always quite limited to situations where you have your stationary, your stationary state. We also looked at, this is the second point that I haven't touched today. You can also think about in team sports that you don't have a soccer. So in Elo, what you assume is that your entire team gets a rating. However, you could, for example, assume that if I have a team sport, that you have it's set up of a number of players, and each player has a distribution and a certain mean strength, and then this gives you a distribution for your team of your strength. You can generalize this for Elo to a certain extent. If you really want to do that, then and if you are in the gaming community, you actually use the Glico system, which is not Glico, and what's the other one? There's a second one. I don't know. So if you play Xbox, you probably know it. What was the other one? Actually?
I don't remember the name.
But there are other plays. But we thought about this. But yeah, this is a bit more hidden in this paper. And with this, I would like to thank you for your attention. And there are the references if you want to have a look at the work.
questions?
Does the relative entropy decrease for uniform condition, or is it for a specific condition?
So you mean the plots that I showed you here? I started out with a uniform initial condition. I don't think it would behave any different if I start with. Why should that change? I haven't tried, to be honest, but I would expect that it should decrease as well. Yeah.
And sigma is important.
In the, I mean, if I turn this in the sense, yes. I haven't played how pronounced this effect is for different values of sigma. It's definitely interesting. The larger the sigma, I guess, the less pronounced. Because it's always, isn't this like relating to transport versus the two transport operator pushing towards the different equilibrium, like the equilibrium in the r and the rho direction in this case. So yeah, when I only did it for one, so yeah, definitely interesting.
I get so when you do the shifted Elo system, you never see the growth of the first moment of the rating.
So for the if I shift it, then no, because it's shifted in this. So you never have this rating. So you kind of turn off you always go back to the reference frame, because otherwise, I mean, you know that you have this linear growth due to the assumption that you have. So you turn off the learning effect, or you just put it always back. So that is the little trick that is done. One could, for example, and if you look at Elo-type A models, if you don't play as a player, usually you lose after a while strength. So one could include some kind of decay effects in here. Haven't done that yet. So there are possibilities, yeah, lots of them, I would say.
Oh, sorry. I just had another question that's less of a mathematical nature, actually. Do you know what system Formula 1 uses?
Formula 1? Oh, no, but I don't think it's the Elo.
Yeah, sure, but
so there are a few. So I was surprised that yeah, for gaming it's Glico and this kind of thing. And what's the other one? I
Skill?
What?
True skill?
True skill is the one for, but I have no idea what is done for Formula 1.
How does one use a relative entropy for the existence of a steady state? Is it the minimizer?
Yeah, I mean, it gives you a priori estimates that you can use, and then you can bound moments. So this is how you usually use it in this case, and that's what Untitled did. But for the existence of minimizers, I don't know how to use it in the hypercoercivity. I'm not the hypercoercivity expert. You have to ask Joanne. I mean, well, she knows quite well what she wants, and she can't get it. So at least she didn't succeed so far. Yeah.
So I thought your model with the rho, with the learning, is an extension of Japan and Jinka.
Mm-hmm.
So in that case, if you put your rho to be constant, like it's like turning off the learning,
Mm-hmm.
don't you go back to their?
Yeah, then I go back to Shibani.
But in that case, like they have a convergence to a steady state, right? So does their steady state also serve as your steady state?
Yeah, but they don't have the yeah. So if I turn off the diffusion and I have no learning, then it's exactly Juncker and Shibani. But if you, for example, add some diffusion, then everything from Juncker and Shibani doesn't work either, because you get this blurring in the y direction, and then all the results also don't hold. So I think as soon as they would introduce some kind of diffusivity or variation in the rating, then nothing is known. But if I turn them off, I get all the way back to your yeah.
But if rho is a constant, how does the diffusion affect things?
No, but if I assume that I have so if rho is, yeah, but in this case, if I add this, so if I would just assume I have no learning in my, but just a little bit of diffusion in my ratings. So my ratings are my strength is not increasing, but I assume that every day I have tiny fluctuations. So I have a constant value plus a tiny fluctuation. This would give me a little bit of blurring, and then the steady state results control data for the information.
I see. I have another question about, you said you cannot control the tail at infinity. If you start with something that is well controlled at infinity for the tail, so can you show that it propagates decay?
So we assumed that that our initial data is a probability distribution. So we didn't assume in the proof that it's behaves very well at infinity. That's a good question. If this is enough, I would have to check with Joe. But yeah, the problem was in principle that the confinement terms or the transport terms in rho and in R, they get small as you tend to infinity or weaker. And if you don't, maybe if you start with this assumption, one could, but I have to ask.
Like you just start with something compactly supported, for example.
Yes, I have to ask maybe 100 volts there.
If no more questions, then let's thank Marie-Therese again.